What's up, everybody? This is Coach Sharp. Welcome back to my Algebra 2 / Advanced Algebra notes videos. Today, we got a relatively short video. Um, this pairs with our discussion on normal distributions and standard deviation. We are going to talk about z-scores. So, let me pull up this whiteboard first of all. Okay. Um, so in the notes, I basically just showed this formula, which I'm about to write. But what a z-score is, did have the definition up there. It's the number of standard deviations away from the mean that a data point is. How many ever standard deviations away is your z-score? Let's actually try to make a line. So we got a line. Curve might be a little wonky here. Let's see. Yeah, it's very wonky. I'm not going to sit here and try to make it perfect. But there we go. All right, so we got a curve that's a normal distribution. We got our mean in the middle. Then we go out 1, 2, 3 standard deviations. And then we go -1, -2, -3 this way. So the example that I did in the notes was about the test score. So if we had a mean test score of 80, the standard deviation was 6. We would add 6 3 times going that way, subtract 6 3 times going this way. So if your actual test score was an 86, you were 1 standard deviation away from the mean. Your test score of 86 had a corresponding z-score of 1. If you had a 71, purple, you had a 71, which is halfway between 74 and 68. Your z-score would be halfway between -1 and -2, which would be -1.5. So with the normal distribution, we could do some basic scores, some basic data points rather, and get some basic z-scores. But it's not always going to be this simple, okay? So instead, we have a formula that we are going to, I'll give y'all a second to get that down because I'm about to clear the page. Pause the video if you need to. There's a formula that we are going to use instead. Okay. I wrote the formula a couple different ways. We have x minus mu divided by sigma. Okay. So that was using the lowercase mu, which represents mean, lowercase sigma, which represents the standard deviation. If y'all remember from the Khan Academy video that we watched, and the link for that Khan Academy video is also in this assignment on Canvas. However, if we want it more written out, we can also use this equation. Our data point minus the mean over the standard deviation. So both formulas tell us the same thing. The blue one just kind of basically explains the purple. Okay. So those formulas will allow us to calculate the z-score for any data point if we know the mean and the standard deviation. All right, so let me close the whiteboard. Now I'm going to share. We're going to jump into the Desmos activity. All right. So again, we have this lady, Miss Anchor, and let's talk about her and her twin brother. Okay. So do my head up. There we go. She's 5'11" and her twin brother is 6'5". So we're trying to see who's more impressively tall. Z-scores will allow us to compare. I'm not going to go into it in the video because it's not relevant to your homework. But if you were here in class, we could actually convert a Z-score to a percentile. Like when you go to the doctor and they say your height is in whatever percentile, your weight is in whatever percentile. Or if you take a test, a standardized test, your test score is in whatever percentile. When it says whatever percentile, that basically means you scored higher than this many people. Okay. We kind of did something similar. I have somebody's worksheet here with me. On this worksheet with the normal distribution, one of the questions on the first one says, what is the score of a person who scores higher than 84% of the people? I'm blocking the face. Sure how's that. What's the score of a person who scores higher than 84% of the people who take the SAT? So what score puts them higher than 84% of the other people? So that SAT score is at the 84th percentile, but it would also have a Z-score, a certain number of standard deviations away it was from the mean. If a Z-score is higher, if one Z-score is higher than the other one, the percentile is going to be higher than the other one as well. Okay, so they tie hand in hand. So if the Z-score is higher, the percentile is higher. So one Z-score might, if you had a Z-score of these are actually true, so I'm not pulling them off the top of my head, but if you had a Z-score of +1, that was actually the 84 percentile I was just talking about. And if you had a Z-score of 2, so you were 2 standard deviations above the mean, you are in the 97.5 percentile. Your height, your test score, whatever, is better than 97.5% of other people. So we could turn them into percentiles, but again, we're just going to focus on the Z-scores. So that's kind of what the question's asking though. What, is her height being 5'11", does that put her in a higher percentile for women than his does being 6'5" for a man? That's what it was asking. I kind of did a hand pull in class, and most of y'all said the woman being 5'11" is more impressive. So we're going to calculate the Z-scores to see if that's true. Okay. So here's the formula again right here. Y'all already wrote it out. Okay. Over here on the left, we have the average height and the average standard deviation for a woman and for a man down here. Okay. There we go. So we're going to do this formula for her. It said she's 5'11". Okay. Y'all need to take note of this because you're going to have to do it on one of the problems on the worksheet. She's 5'11". Okay. So we have to convert that to inches. Multiply 5 times 12 because there's 12 inches in a foot, which is 60 plus 11 is 71 inches. Okay. He is 6'5". Let me change the color. He's 6'5". You can go back to the last screen, or you can rewind the video back to the last screen if you need to see it to double check. 6 times 12 is 72, plus 5 is 77. Okay. So we had to convert feet and inches to just inches. There's one problem you have to do on the worksheet where you have to do the same thing. You have to convert feet to inches. So we're going to do hers first. Okay. So we're going to use her 71. So her formula, her data point is 71 minus the mean, which is 63.8. divided by the standard deviation, which is 2.8. Okay. The one thing I need y'all to note, and I do have one of these calculators handy. Good. So if you're using this calculator, using the calculators that we have in class or most scientific calculators, if you have the ability to put in the entire expression at once, okay? So if I was trying to type this into this calculator, okay, it would look like this. Let me change colors. It would look like 71 minus 63.8. You hit divide, it's going to give you that 2.8. Okay. Problem with the scientific calculator is it's programmed to do order of operations. So if you type this exactly, what it's going to do first, it's actually going to divide 63.8 divided by 2.8, which is 22.79 if we round it up. And then we subtracted that from 71, we would get 48.21, which is definitely incorrect. Okay. So what you have to do is if you're punching in this calculator, you have to put the numerator in parentheses because it'll do what's in parentheses first and then divide it by 2.8. So that's the key you got to remember. Put this numerator, whatever minus whatever in parentheses. So you type this in. If you're using an iPhone calculator or if you just want to go one step at a time, you can subtract that and hit equals, which would be 7.2, and then divide that by 2.8. But what you're going to get is 2.571. We can go to 3 decimal places. If you just did 2, that's okay, but I'm going to go to 3. 2.571. Okay. Now, if we did her brother, again, same formula. We got 77 inches minus 69.3, so just over 5'9", the average height for a man, divided by 2.92. You get that. I believe it is 2.637. Let me actually do it since I've calculated me instead of sitting here questioning my video. 2.6369. Yes, so 2.637. Okay. So there's the 2Z score. So, surprise, surprise, said most of y'all pick Miss Anchor for being more impressively tall for a girl, but her brother's Z score is slightly higher. Okay. If we actually converted this to a percentile, there was a chart that I showed y'all in class that does it. Her Z score would put her in the 99.49 percentile. Maybe some of y'all understand the percentiles better. So she's taller than 99.49% of other girls. But his Z score is 99.59. So he is taller than 99.59% of other guys. So he is, comparatively to the other guys, slightly taller than she is compared to the other girls. Okay. All right. Pause that if you need to. I'm going to clear this out and move on. See, there's her Z score. I told you we got it. Okay. All right. Now, we had a fun little discussion with this in class. Who's the GOAT? Wilt Chamberlain, Michael Jordan, or LeBron? I didn't need to click on it. Can you actually click on this? I didn't do anything. Didn't really get much objection. It says, "Are you bothered that Kobe didn't make the list down below?" That's usually the one name people shout out, but the metric that we're using, which is it's subjective, you can pick whatever metric you want, but we're going to compare career points per game versus the average player during their best era, their best decade. So Wilt Chamberlain is going to be the 1960s, Michael Jordan the 1990s, LeBron the 2010s, and see how much higher than average their points per game is than the average player. Okay. So moving on to the next slide. All right, we're gonna do 3 calculations real quick. I did this exact same thing in class. Okay. So Wilt Chamberlain. We've got X, his mean is 30.1 points per game. His mean, the mean of the other players is 10.8 points. And the standard deviation is 7. Okay. MJ will be red because of Bulls. His mean is also 30.1 points per game. While I'm writing these down, his mean is 8.7. I'll talk about it in a second while I'm transitioning to LeBron. And then his standard deviation is 5.9 points per game. There's a couple things I mentioned. You got to take into account the eras. During Wilt's era, there were less players on the roster, so that means less players to spread the points around in. So that's why it was a higher average. It doesn't mean they were better. It doesn't mean there were better players in the 60s than there were in the 90s or 2000s. Certainly. That's really the main difference. There's a couple other factors in there as well, but that's honestly the main difference. LeBron, I'm gonna say during the 2010s, I guess you would associate him getting back with Cleveland more than you would the Heat or certainly the Lakers. So I'll do the maroon red for the Cavaliers. So LeBron, his average is 27.1 points per game. The mean for the players in his era was 8.4. And the standard deviation was 5.5. Okay. So let's see if I can write this small. So Wilt's equation would be 30.1 minus 10.8 divided by 7.0. And you would get 2.757. MJ. I'm going to do his down here and I'll do LeBron's on the side, I guess. 30.1. So same average, lower mean, and a lower Z-score. 30.1. That clarify that a little bit. It's a little wonky. 30.1 minus 8.7 divided by 5.9. That looks a little better. You do his, you actually get 3.627. And then LeBron, we do his, you got 27.1 minus 8.4 divided by 5.5. And this one, I believe you get right at 3.4, if I remember correctly. Yes. All right. So the highest Z-score belonged to Michael Jordan. So that proves what my personal argument would be, that he is the greatest player of all time. He is better than LeBron. He is better than Kobe. He is better than everybody else. That is a personal opinion, but my opinion is correct. All right. So y'all just saw 5 examples of Z-scores. On the worksheet, I know it's going to be flipped on. Well, it's flipped right now, but then I think when the video uploads, it flips back. So y'all might be seeing it correctly. The worksheet is 8 word problems. 6 of the 8 have 3 numbers. Okay. Sixth day to have three numbers, all three numbers that you need to fill in the formula. All 8 problems say mean or average. So if you look at number 1, let me try to get my finger on it. It says average. Average is the mean. So it says the average is whatever, the mean is whatever. That's your mean / average. They all say standard deviation. There's not a concise way to say standard deviation other than standard deviation. So they all say the standard deviation is whatever. And then if it's just 3 numbers, the third number is your data point. There's one problem that has 3 numbers, but it was like I mentioned a few minutes ago. 2 of the numbers are in inches, and 1 of the numbers is in feet. So you have to convert the feet to inches. And then one problem, there's actually 4 numbers. Okay. 3 of them are the numbers that you're going to use. They all have the same unit of measure. And then the 4th number is just, it's descriptive, but you're not actually using it in the problem. Okay. So you got that worksheet. You also got this one, which we had the separate video, which is in the assignment on Canvas. Both worksheets are a separate grade. You need to get them done and get them turned in ASAP. If y'all got any questions, send me a message and remind. Otherwise, I will see y'all in class.